board. Okay, so this is now being recorded, and if you have, just a reminder, if you have any questions, you can chat in the chat box. You can also go to the Q&A box to type in your questions as we go through the presentation. So what we're going to be looking at are the objectives for this webinar. First of all, we're going to define words related to the mass of power. We're going to perform calculations related to the Bantoff power distribution, and we're going to also look at the Shapley-Shubik power distribution. And I'm going to pause the recording for a moment. Okay, so it's now recording again. So these are the objectives, these three objectives that we're going to be looking at for this session. One thing I'd like to mention is that the vocabulary related to the mass of power is very long, to say the least. There are a lot of words, and if you go straight to the homework without understanding the vocabulary words, it is going to sound like a whole foreign language. So the first thing we need to do is define all of the vocabulary that is related to the mass of power, and then we can do the calculations. Okay, so first thing this mass of power is related to something called a weighted voting system, where each voter does not necessarily have the same voting power, where different people might have a different weight to their vote. And an example would be the chair of a committee may have 2 votes, while each member of the committee may have 1 vote. And so it's because of the chair having, I guess, a more important role, they get more votes. So for the purposes of this chapter, we're going to say each vote is either a yes or a no, where there's a resolution to be voted on, and everyone gets to vote yes or no. With enough votes of yes, the resolution passes. If there's not enough votes of yes, then the resolution fails. So that's the type of situation we're going to be looking at. The voters are called players, and they are noted with the capital P with a little subscript. And the subscript that you see here is just saying basically first player, second player, third player, and so on. And the weight of the player is the number of votes that the player controls. And so those are lowercase w's for each weight. So W sub 1 is player 1's weight, W sub 2 is player 2's weight, and so forth. So each player is assigned a weight, and the capital letter V is used to represent the sum of all the weights. So if you're going to add weight 1 plus weight 2 plus weight 3 plus weight 4 and so on, all the weights, that sum would be represented with the capital letter V. Now the quota is the minimum number of votes needed to pass a motion, and we use a lowercase q to represent quota. So as an example, if there are 3 players with weights 3, 4, and 5, and the quota is 8, the notation would look like this with the bracket, and then 8 : because 8's the quota, and then the players or weights are listed after that. So the capital V would be the sum of the weights. So in this case, capital V is 12. Q is 8 because that's the quota, and then weight 1 is player 1, which is 5. The weight 2, which is for player 2, that's 4. Weight 3, which is for player 3, that is 3. So a player is a dictator, some more vocabulary, if the player's weight is greater than or equal to the quota. So in this case, player 1 has a weight of 5, and the quota is 5. So player 1 is considered a dictator because basically if player 1 wants the resolution to pass, all player 1 has to do is vote for the resolution and it gets passed because player 1 has a weight that's greater than or equal to the quota. The votes of the other players aren't needed to pass the motion, so that's why it's called a dictator situation. So in this case, player 1 would be a dictator. If the player is not a dictator, but a motion can't pass without his vote, then the player has what's called veto power. This player cannot force a motion to pass, but can force a motion to fail. So if the player has veto power, then the following inequalities will be true. So both of these inequalities have to hold in order for a player to have veto power. So that player's weight would first of all have to be less than the quota, because if it's greater than or equal to the quota, he's a dictator. So to have veto power, the weight has to be less than the quota, and the sum of the weights minus that player's weight has to be less than the quota. So if both of these inequalities hold true, then that player would be considered to have veto power. Okay. So here's an example. We have a situation where the quota is 12, and the player 1 has a weight of 9, player 2 has a weight of 5, player 3 has a weight of 4, and player 2 has a weight of 1. Sorry, player 1 has a weight of 1, 2, 3, and 4. Player 4 has a weight of 2. So if you add them up, you get 20. So capital V is 20. So let's determine if player 1 has veto power using the inequalities. Player 1 has a weight of 9, which is less than quota. That's true. 20 minus 9, the capital V minus the weight is less than 12, is also true. So since both inequalities hold, player 1 has veto power. Player 2 does not have veto power because even though 5 is less than 12, 20 minus 5 is not less than 12. Player 3 and 4 do not have veto power for the same reason. Even though the weight of 4 is less than 12, the weight of 2 is less than 12, when you subtract 20 minus 4, you get 16, which is not less than 12. 20 minus 2, which is 18, not less than 12. So in this situation, player 1 has what's called veto power. So by looking at just the weights of the distribution, looking at the weights, the distribution of power can be deceiving. For example, in this voting situation, each person would need to vote yes for the motion to pass. If we take a look at the quota of 19, and the weights are 8, 7, 3, and 2, they all have to vote yes to meet the quota of 19. So since that's the case, something to consider is, does P1 really have more weight than player 2? Player 1 has a weight of 8, player 2 has a weight of 7, but when it comes to making a motion pass, like having it carry where it meets the quota, the difference between the 8 and the 7 isn't really that different because all 4 players in this case have to vote for the resolution for it to pass. So the fact that they have different weights really doesn't make a difference. So how can we determine who has more power than another player? So we need a way to measure the true power of the players, and we're going to discuss 2 methods for this. The Banzhaf power distribution is one of them, and the Shapley-Shubik power distribution is the other one. So I'm just checking real quick to see if there are any questions before we move on to these calculations. Okay, I don't see any questions. So basically, I've defined a lot of the vocabulary that goes along in general with the math of power, and now we're going to take a look at how to perform calculations to really truly measure who has more power than somebody, which players have more power. And these two different methods, it's not like one method is better than the other, they're just different ways of looking at the situation to see who has more power. Okay, so the first one we're going to look at is a Bontoff power distribution, and we have more vocabulary words that go along with each of these distributions. So we have the general vocabulary words that we've already talked about. Now with Bontoff power distribution, there'll be some other vocabulary words, and then the same thing with the Shapley-Shubik power distribution. So a coalition, when we're looking at the Bontoff power distribution, a coalition is any set of players who might join forces to vote the same way. So how we write this is with curly braces, and the players listed in the coalition have a comma between them. So it looks like this. This would be a coalition, this one is a coalition, this one is a coalition. And the order that the players are listed in the coalition is not important. So like this one here, not in numerical order, makes no difference. If I rearranged the players, so it said player 1, comma, player 2, comma, player 3, it would be the same exact coalition. So the order that you have the coalition, the players written in the coalition does not matter. So those are coalitions. A winning coalition is a coalition that has enough votes to pass the motion. Because you can form coalitions different ways, but that doesn't mean they have enough votes to pass. It doesn't mean they have enough votes to meet the quota. So the winning coalitions are the ones that have enough votes to meet the quota, okay? In a winning coalition, a critical player is a player whose vote is needed to pass the motion. So that would be where you're looking at the coalition, it's a winning coalition, and if there's a player that if you took them out, it wouldn't pass, that's a critical player, where that player has to be in that coalition for it to meet the quota. And there's another inequality. I know there's several inequalities through this lesson, so it might be good to have like a reference page of just writing down this inequality is for dictatorship, this inequality is for veto power, and so on. It can really help as you're trying to work the homework problems. That's a suggestion to have all these inequalities handy, because we have another inequality here that goes along with the critical player. The critical player is a player whose vote is needed to pass the motion, and this inequality notes that. So the capital W is the weight of the coalition. So you add up the votes in the coalition, and if you subtract the weight of the individual player, the lowercase w is the weight of the individual player. So if you take the sum of the coalition minus the weight of the individual player, and if it's less than the quota, that's a critical player. So it's a lot of subtraction with comparing with the quota to see which players in a coalition are critical players. Now, once you have, let me go back to this. When you determine who the critical players are, it's a good idea to just underline them, because then you can keep track of who are the critical players in which coalitions. And it's possible to have more than one critical player in a coalition. So just because you found a critical player in a coalition doesn't mean you stop there. You still have to look at the rest of the players. And it's a good idea to like underline who the critical players are so you can keep track, because you have to find each player's critical counts. You look back to see how many times was player 1 a critical player. That's player 1's critical counts. Then you look back at player 2. How many times was player 2 a critical player? That's player 2's critical count. So for each player, you need to find their critical counts. That'd be how many times each of them was underlined. If you underline them in the list, that really helps. And then capital T represents the total of the critical count. So let's say you have 3 players. Each player has a critical count. You add the 3 numbers together. That is the capital letter T. So add the critical counts of each player to arrive at T. Now, the Bantoff Power Index is the ratio of the player's critical counts to the number T. And to find the power distribution, you list the indexes. Now, because some students get confused between Bantoff Power Index and Bantoff Power Distribution. The index is for each player, you write the ratio of the critical counts over T. The Bantoff Power Distribution, all that is basically listing altogether each power index. So you find the power index for each player, and if you list them all next to each other, that's called the power distribution. So to find the power distribution, you're not really doing any calculations. You're just listing all of the Bantoff Power Indexes together. So it just depends on the wording. If it wants you to find the Bantoff Power Index for player 1, that's going to be writing 1 ratio. If the website wants you to find the Bantoff Power Distribution, then it's going to ask you for all the ratios. That's the only difference there. Okay, so here's the steps for computing the Bantoff Power Index. First, you make a list of all the possible winning coalitions. Now, you may not be able to just glance at the situation and know off the top of your head what the winning coalitions are. So you might want to list, a suggestion would be is if you list all the coalitions and then cross out the ones that are losing. That might be a systematic way to go about that. So basically, coalitions are all the ways you can arrange the players. So if you have 3 players, well, one of the coalitions would be where just 1 player is in the coalition, and then you would list those with just 1 player inside the coalition. And then what about 2 players? What about 3 players? What are the different ways you can do that? And we'll do an example so you can see this. But basically, all you're concerned with are the winning coalitions. So the ones that are losing, you can just cross them out. And then with each winning coalition, you underline the critical players using that inequality, capital W minus lowercase w is less than Q. And then the critical count, all you have to do is add up how many times each player was underlined. So each player will get a critical count, and that's by adding up how many times that player was underlined. And then find the capital letter T by adding up the critical counts. And then compute the power index for each player by taking the critical count for that player divided by T. Now, pay close attention to the MyMathLab directions because sometimes they're going to ask for a simplified fraction. Sometimes they may ask for a decimal, and I don't know why, but it's not always consistent with that. So be very careful, like next to the box on the screen, if you look below the box, you will see the directions on how to enter in the numbers, because if you go through all this trouble and you get to step 5 and you type in 3/6 when it wants a simplified fraction of 1/2, MyMathLab will mark it wrong even though you went through all these steps correctly. And then what you're thinking is that you went through the steps wrong because it's just something new and may not realize that all you had to do is write 1/2 instead of 3/6. So be careful how you're putting that in MyMathLab, that it's how the directions are stating. Okay, so here's an example. We'll go through the 5 steps. Step 1. For this particular example with player 1 having a weight of 5, player 2 has a weight of 4, and player 3 has a weight of 3, these are the winning coalitions for a quota of 7. Okay, player 1 plus player 2 is 9. That meets the quota of 7. See, this has a total of 9. Player 1 plus player 3 has a total of 8, so that meets the quota. Player 3 plus player 2 has a total of 7, which meets the quota. And then when you add all 3 players, you get 12, which also meets the quota. So these are the coalitions in this situation. There's 4 different ways to have a winning coalition. So now, step 2, we're going to find the critical players in each coalition. So I look at the first one from up here. Look at that one. And remember that capital W is the sum of the weights, which would be 9. And this is the inequality that you use to determine if that inequality is met, then that player is a critical player. So I take 9 minus 5 is less than 7, so P1 is critical player. 9 minus 4 is less than 7, so P2 is critical player. So if you notice, I underlined P1 and P2 because they are both critical players in this winning coalition. Okay? Do the same thing for the second winning coalition that has a capital W of 8. So I did 8 minus 5, which is less than 7. 8 minus 3 is also less than 7. So both of those are critical players. So if you notice, they are both underlined as well. The next winning coalition has a capital W of 7. 7 minus 3 is less than 7. 7 minus 4 is less than 7. So that means both of those are critical players. They've also been underlined. The last winning coalition has a capital W of 12. Well, 12 minus 5 is less than 7. That's not true. So player 1 is not critical. 12 minus 4 is less than 7. That's not true. Player 2 is not critical. 12 minus 3 is less than 7. That's not true. So player 3 is not critical. So for the last winning coalition, nothing is underlined. So it's possible to have a winning coalition where there's nothing underlined or more than one player underlined. You just have to look at each individual winning coalition and each individual player within those winning coalitions. Okay, so it's a little bit tedious in that way. Can't really get around that. So, okay, so now step 3 is I go back and add up how many times each player was underlined. So if I look back, player 1 was underlined here, and player 1 was underlined here. So player 1 has a critical count of 2. Player 2 is underlined here. Player 2 is also underlined here. So player 2 has a critical count of 2. And then player 3 underlined here and here. So player 3 also has a critical count of 2. So for each of those players, they have a critical count of 2. So that's step 3 in our process. Step 4 is to add all the critical counts. That gives me 6. And then step 5, I'm writing my ratio. For this symbol right here, that's Bon-Tov Power Index for player 1, which player 1 had a critical count of 2. Capital T is 6, which reduces to 1/3. Bon-Tov Power Index for player 2 had a critical count of 2. Capital T is 6, also reduces to 1/3. And the same thing happens with player 3. So we have found the Bon-Tov Power Index for each player. And if the website says to write the Bon-Tov Power Distribution, that just means it wants all 3 of those. There'll be a spot for you to write all 3. John Bon-Tov in 1965 argued that the critical count, not the weight, measured the player's power. Notice how the weights are different, but the Bon-Tov Power Indexes are the same. Okay, so let's go back to the original problem. Notice how player 1 has a weight of 5, player 2 has a weight of 4, player 3 has a weight of 3. Makes you think that player 1 actually carries more power than the other 2. But if you look at the Bon-Tov Power Index for each one, you get 1/3 for all of them. So what John Bon-Tov was saying is that this is a much better way to measure who has the more power. So according to the Bonsov Power Index, all three players have the same power, even though they have different weights. And just to note, if a player with zero, if you have, it is possible for a Bonsov Power Index to be 0, and if that's the case, then that player is called a dummy player. That's a technical word. Sounds bad, but that's really what that player would be called, okay, if they have 0 power. They might not have 0 weight. They might have weight, but have 0 power when it comes to the Bonsov power distribution. So before we move on, I'm going to check the chat box and the question and answer box to see if there are any questions here. I don't see any questions. So I'm going to continue on. Note that when the number of players increases, there will be more work involved in step 1, which was finding all of the winning coalitions. A good strategy for making this list is to make a list of all the coalitions systematically so you don't miss anything, and then look at each one individually and just cross out the ones that aren't winning. So keep that in mind as a suggestion when you're trying to find all of the winning coalitions. Okay, so now we're going to move on to the Shapley-Shubik power distribution. In 1954, Lloyd, Shapley, and Martin Shubik proposed that votes are cast sequentially. Thus, the order that the coalitions are formed make a difference. So they're trying, again, to try to see who has the most power, but they just had a different method for determining that same, that same goal. The same goal of who has more power in this situation, but they had a different method. They looked at it as voting in sequence, meaning that the order of the players voting makes a difference. So in this case, player 1, player 2 is not the same as player 2, player 1. Also note the notation is different. For the coalitions that we did with the Bonsov power distribution, there were curly braces for listing the winning, the winning coalitions. Here, we're using these other types of symbols around the list to indicate there is something different about it, that the order does matter. Okay, something that we need to define with this type of power distribution is something called a factorial, because we run into this with this calculation. When you have an exclamation point after a number, it's called factorial. So 4 factorial would look like this, 4 with an exclamation point. And what that means is you're going to multiply starting with 1 up to that number. So 4 factorial, 1 times 2 times 3 times 4. If you have something like 5 factorial, that would be 1 times 2 times 3 times 4 times 5, and so on, okay? There is a factorial key on, like, every scientific calculator out there. So play with that on your calculator. Make sure that you understand how your calculator works. Some calculators you have to type the 4 and then the factorial key and then equals. Other calculators, you might just type 4 factorial and not have to hit equals. Like, play around with your calculator, make sure you know how that works. You know that 4 factorial is 24. So if you see 24, if you type in 4 factorial, you see 24, then you know you did it right. And so just be watching out for that. Sometimes a factorial might be under like a probability menu. You might see a button on your calculator that says PRB. And if you click on that, you might see a menu come up and a exclamation point might be on there. If you have trouble with your calculator, contact your instructor, tell them what make and model calculator you have, and they'll be able to help you out. So, but we will be using this calculation in this power distribution. Okay, so how does this power distribution work? Well, if the weighted voting system has n players, then there are n factorial sequential coalitions. We are not interested in necessarily winning coalitions. It's not like the other one where we're only looking at winning coalitions. Here we're looking at all sequential coalitions. So if there are 4 players, there are 24 sequential coalitions. In every single problem with 4 players, there are 24 sequential coalitions. The good news is that once you see the list of 24, you can really just use that same list over again in every other problem that has 4 players because it's the same list, okay? So when we read a sequential coalition, you read from left to right and then add the votes as you go from left to right. And the first player to meet the quota is called the pivotal player. So in every sequential coalition, there can only be one pivotal player. And once you reach that pivotal player, we're going to underline it and then not add the rest. Okay, so an example would be this one where you have a quota of 7 and you have a sequential coalition of 5, 4, 3. Player 1 does not have enough to meet the quota, so you add player 1 and player 2, which gives you 9, which does meet the quota. So that means player 2, I'm going to underline it, is the pivotal player in this sequential coalition, okay? So this is just an example of what I mean by adding from left to right and trying to find the pivotal player. The number of times a player is a pivotal player is that player's pivotal count. That's why we're underlining them, because when we're all done, you go back and look at everything that you have underlined, and you're going to add how many times was player 1 underlined, how many times was player 2 underlined, and so forth. And that would be that total number of times that player's underlined is that player's pivotal count. And the total pivotal count for all players is always n factorial. So if there's 4 players, then the total would be 24 because there are 24 sequential coalitions with 4 players. So the Shapley-Shubik power index for each player is that player's pivotal count over the n factorial number. And the list of all of the power indexes is the power distribution. Just like before, each player gets a fraction, and then if it's asking for the power distribution, that's just listing all the fractions next to each other. Okay, so here are the steps for calculating the Shapley-Shubik power index. First thing, you want to make a list of the sequential coalitions. So if there are 4 players, you need to have a list of 24 sequential coalitions. But like I said, you don't have to regenerate this list for every problem. Think of it this way also. If there are 3 players, 3 factorial is 6. There are 6 sequential coalitions. So, but it's the same 6 every time. So once you have that list, you can just keep reusing it. A great place to get the list is to look either in the book or in like a help me solve this in the math in the homework. It'll list for you in the view an example or help me solve this in the homework or in the book. It lists all for 3 players, the 6 sequential coalitions, for 4 players, all 24 sequential coalitions. So you do not have to generate this list on your own. You just copy it from somewhere and just reuse it, okay? Then for each sequential coalition, underline the pivotal player. There should be exactly 1 underlined for each coalition. Then you want to find the pivotal count for each player by determining how many times each player was underlined. And then you compute the index by taking the pivotal count and putting it over the n factorial number. So if there's 3 players, n factorial is 6. If there's 4 players, n factorial is 24. They probably won't go much higher than that because then you get into a lot of sequential coalitions. Okay, so let's do one with 3 players so that n factorial is only 6. 1 times 2 times 3 is 6. So these are the sequential coalitions. So you take the 3 players and you just write them in the 6 different ways, rearranging the numbers. So those are all of the sequential coalitions for this example. And I'm going to pause here before we get into the example and just see if there are any questions. I don't see any questions. Okay. So that's step 1, listing the sequential coalitions. Next step, I'm going to underline the pivotal player in each. So remember that the quota is 9. So for the first one, 7 plus 6 is all I need to reach 9, so I stop there, underline the 6. For the second one, 7 plus 2, that's all I need to reach 9, so I underline the 2. The next one, 2 plus 7, I don't need to go any farther to reach 9, so I underline the 7. The next one, 2 plus 6 plus 7. Well, I didn't reach 9 until I got to that 7 right here, which is why I underlined it. The next one, 6 plus 7, that's as far as I need to go to reach 9. And the next one, 6 plus 2 plus 7, I had to go all the way to the 7 to reach 9. So that is how we determined the pivotal player in each. You add from left to right until you reach the quota. The quota here was 9. As soon as I reach the quota, I stop and underline the player. Okay, so now we need to find the pivotal count for each player. So that just means going back and looking at the list to see how many times was player 1 underlined, player 2, and so forth. And if you notice, player 1 was underlined 4 times, player 2 was underlined once, player 3 was underlined, player 3 was underlined once. If we look back here, 4 times, yep. So that would be the pivotal counts for each player. Pivotal count for player 1 is 4. Pivotal count for player 2 is 1. Pivotal count for player 3 is 1. Okay, so now we're going to compute the index for each player. Player 1, first of all, notice that the bottom number for all of these is 6. That's because n factorial, which in this case is 3 factorial, is 6. So that is always the bottom number in my index for the Shapley-Shubik index. And the top number, that's the pivotal counts for each player. Now notice that in this case I had to simplify the 4/6 to 2/3. Just a reminder again that when you type this into my MathLab website, if it's asking for a simplified fraction and you type in 4/6, it will mark it wrong, okay? So you want to make sure you type in 2/3 if the directions specifically ask for a simplified fraction. Okay. Notice that players 2 and 3 have the same index, even though player 2 has a weight of 6, player 3 has a weight of 2. You would think that player 2 has 3 times the power as player 3, because you take the weight of player 3 times 3 gives you 6. Player 2 might start feeling good about himself because he has 3 times the power of player 3, but not really. This is where the weights can be deceiving, because when you're doing a calculation like this with the Shapley-Shubik power distribution, notice that player 1 has twice the weight of player 2, sorry, not twice the weight, 4 times the weight of player 2 and 4 times the weight of player 3, but players 2 and 3 have the same index, same power index. Also notice that when you add up these fractions, you get 1, because it's basically saying there's 100% of the power. How are we distributing 100% of the power? Well, player 1 gets 40%, 4/6%, player 2 gets 1/6 out of the 100%, and player 3 gets another 1/6 of it if you divide it into 6. Okay. Note that you can reuse the same list of sequential coalitions for different problems. Like I said, this list had 6 sequential coalitions. Another problem with 3 players will have the same type of list. It's just instead of the numbers we had, which were 7, 6, and 2, another situation might not use 7, 6, and 2, might use 3 different numbers, but the structure of the list would look exactly the same. Same thing with 24 sequential coalitions. Find an example of this in the book or in the homework, and then just use that same list of sequential coalitions for every problem with 4 players. Okay, you will just need, so in that case, you can use the same list, you just need to change the underlying players for that. Okay, so in this webinar, we discussed definitions related to the math of power and also perform calculations with the Banzhaf power distribution and the Shapley-Shubik power distribution. So I'm going to look again in the question and answer to see if there are any questions out there before we wrap up. Okay, so if you have any questions, there's my email address. Like I said, I will take this, my notes from this presentation and mail them to all the MAT 116 instructors to distribute. So, but you can also email me and I would reply with the notes from this presentation, so you don't have to have everything all written down like frantically writing as we're going through. And I just wanted to say this disclaimer. I do this every time. I just feel the need to let you know that this was not intended to cover the entire chapter on the math of power. I really wanted to hit on the things that cause students the most problems, starting with the vocabulary. So many times students get bogged down with the vocabulary that they just get lost. So, and then I wanted to explain what these distributions mean, how to calculate them. I hope the step-by-step process helps as well. But there are things in the Math of Power chapter that I could not get to in this webinar, so this is not meant to replace reading the chapter, watching the videos in my math lab, and so on. So I just wanted to mention that as well. So before we close, I'm going to check one more time to see if there are any questions, and I don't see any. Okay, so thank you for attending, and thank you for your time and your attention with this webinar. I hope that it's been helpful to you. And if you need any clarification after the fact, or you didn't ask their question in this session right now, feel free to email me. I do teach for Liberty Online Math. I've taught this class before, so I'm very familiar with the topic. And thank you again for attending. Have a wonderful day.